Ladies and gentlemen, welcome back. Today we're tackling an elegant problem that appears deceptively simple but hides a fascinating pattern underneath. Let's look at this infinite product as given on the screen. Each factor in the product is in the form 1 plus 1 over n. I need you to note this, that this guy here can actually be written as n plus 1 all over n. I basically made the denominator the same, so I multiply both top and bottom by n. So it is very, very important to note that this can be written in that form. Right. And then we are also told that this product is for n bigger than or equals to 2, which means n cannot be anything less than 2. Right, it must be 2 or more. So now we want to determine all values of n for which the product is an integer value. So ladies and gentlemen, let us add these things. This guy here is going to give us 3 over 2. The next one is going to give us 4 over 3. The next one is going to be 5 over 4. If we had another one, the next one here we can agree that it was going to be 1 plus 1 over 5, right? If you were to add that, you can see it was going to give us 6 over 5. And so on, right? Up until, remember we time seeing here, right? Up until n plus 1 over n. Remember we were told that they are all in that form, but of which we simplify to that form. So now, ladies and gentlemen, I need you to observe how beautifully this telescopes. By telescopes, I mean most terms cancels. I want to show you that here. This 3 on top will cancel that 3 at the bottom. Right? This 4 will cancel that 4. This 5 will cancel that 5. 6 will cancel 6 there. This thing will continue infinitely until we get to the last term. And you can see that on the last term, we are always cancelling the bottom one. You see, the bottom one cancels. So if there's a bracket here, this term at the top will cancel with that one at the bottom. I'm sure you get what I mean, right? And then this one here would have cancelled with that one there. So basically, this product just merely simplifies to the product. The product above just merely simplifies to the numerator. We just left with n plus 1, and then the denominator is 2. And ladies and gentlemen, this is the representation of our product. Therefore, for the product to be an integer, n plus 1 over 2 must be an integer, which means n plus 1 must be divisible by 2, right? And so for n plus 1 to be divisible by 2, it has to be an even number, which implies n itself is odd. Hence, all odd numbers greater than or equals to 3 make the product an integer, because an odd number, which is n plus 1, will be even, and that even divided by 2, we are going to have an integer. So we're going to say n must be an element of odd numbers bigger than or equals to 3, which is 3, 5, 7, 9, and so on to infinity, right? And therefore, n must be an odd integer greater than 2, or you can say greater than or equals to 3. That also works. So, ladies and gentlemen, I'm just going to close here. That is the answer for this question. And there you have it, a neat telescoping product leading us to a simple but elegant condition for integers. If you enjoyed this math journey, don't forget to like, subscribe, and hit the bell for more fascinating maths explanation. Thanks for watching and keep crunching those numbers.